Hello and welcome to Myra. In the last video, we discussed about 2D binary classification and 2D multiclass classification. In this video, we will try to understand multiclass classification and clustering. Multiclass classification. In the previous article, where we took an example of iris flowers, we considered only two features of the flower. But in the real world, this might not be true. We will need more dimension to classify things efficiently. Suppose that along with petal length and petal width, we have data of sepal length and sepal width as well. Now here we have 4 dimensions. Our brain can process up to 3 dimensions accurately. Beyond that, visualizing becomes difficult. For example, in binary classification, we classified flowers as setosa and versicolor based on 2D data. It is easy to plot and see how they are differentiated on the graph. But things might be different in higher dimension, even though data can be classified into different categories as we did in 2D binary classification. Our algorithms are based on mass, and mass does not care about dimension. So do our algorithm. But it does not mean that we should not worry about dimension. As dimension increases, the computational time memory allocated to the algorithm also increases. In the real world, most data have multiple classes, like in the case of classifying fruits, classifying movies based on genre, classifying weather, etc. It might become complicated to build multi-class classifier. So instead we can build a whole bunch of binary classifiers and combine their results to produce a multi-class result. Binary classifiers are simpler and faster than multi-class classifiers. Popular algorithms that can be used for multi-class classification include k-nearest neighbors, decision trees, naive-Bayes, random forest, gradient boosting. In this section, we will be discussing two famous ways of using binary classification to perform multi-class classification. OVR, 1 versus rest. OVO, 1 versus 1. OVR, 1 versus rest. Let us consider 4 classes as shown in the following figure. Now, instead of building one classifier which classifies 4 classes, we can build 4 different binary classifiers which classify each class. For example, class 1 classifies whether an item belongs to class 1 or not. Similarly, class 2 classifies whether an item belongs to class 2 or not, and so on. After classifying all these classes, we put this data in an algorithm which builds boundaries around each class. Now, it might happen that some data points may belong to 2 or more classes. In this case, that data point is run through all the binary classifiers and we look for the class with the highest probability of having that data point. The good thing about this is it is conceptually simpler and faster. The downside is that we have to teach each classifier and classify every input sample for each class to find which class it belongs to. OVO, 1 versus 1. Again, consider 4 classes as shown in the figure. In this case, we will consider 2 classes at one time to check in which class the item belongs to. For example, we have 2 classes, that is class 1 and class 2. Now we will classify the items depending on which class they belong to. If an item belongs to class 1, we will put it in class 1. If it belongs to class 2, we will put it in class 2. After doing this, we will consider another set of class 1 and class 3 and classify the items to their respective class. Similarly, we can go on classifying items in class 1 and class 4, class 2 and class 3, class 2 and class 4, class 3 and class 4. It might again happen that a data point may belong to more than one space. In this case, we look for classes that have majority votes. For example, we can see in the below figure that point came in class 1 for 3 times. So we say that class 1 have the majority of votes. It is clear that 1 versus 1 requires far more classifier than 1 versus rest. But it is sometimes appealing because it provides clearer understanding of how the sample was evaluated with respect to each possible pair of classes. The downside is that as the classes increases, the number of binary classifier increases exponentially, which in result costs the computer memory and time. Clustering. Suppose I give you a bucket full of 6 varieties of fruits and 6 baskets. Your task is to cluster similar fruits in one basket. You will complete the task in minutes. You will not even care about the name of the fruit. Just based on a few dimensions, you will cluster the fruits in different baskets. Humans are pretty good at clustering. Clustering is another method to classify unlabeled data by breaking the data into similar chunks. This method of classification falls under the umbrella of unsupervised learning. Moving further with the above example, again I give you a bucket full of different varieties of fruits, but this time you don't know how many varieties of fruits you have to cluster. But still you complete the task with ease and cluster similar fruits in 6 different baskets. Superb! See how good our brain is. When we perform a similar task on a computer, we need to tell the program how many clusters we need, and that number is represented by k. We say that k is a hyperparameter or the value that we choose before training the system. Our chosen value of k tells the algorithm how many regions to build. Because the algorithm uses the geometric means or averages of group of points to develop the clusters, the algorithm is called k-means clustering. Now the freedom to choose k value is a blessing as well as a curse. If we know how many clusters we have to divide the data into, then simply putting the right k values does our job. It might happen that computer does not put the boundaries at the right place as it does not know where we are accepting the boundaries on the graph. But it might not be the case if our data is sorted with a big space between the clusters. The downside of specifying k value is that we may not have any idea about how many clusters best describe our data. From the above figure, we can see how clusters may get divided if we don't know the right k value. Here k equal to 5 best defines our cluster. But if we don't know the right k value, we might end with one of the above clusters, which will be wrong if we choose any other k value rather than k equal to 5. One good way of eliminating this problem is training our clustering model several times with different values of k and then choosing the value which performs the best. This task of finding the appropriate value of k is called hyperparameter tuning. The only disadvantage is that it takes a lot of computational resources and time. One way to avoid hyperparameter is to analyze data with some visualization tools and then fit the right value of k to our model, or maybe a list of right values of k. This might reduce some time and computational resources. This was all about multi-class classification and clustering. Hope this video was informative. Thank you for watching the video. In the meantime, please like the video and subscribe to the channel.